Suppose we have a random variable that has a Gaussian distribution. When added to another random variable having a Gaussian distribution will provide a Gaussian distribution itself. And this is a well-known fact for the summation of two Gaussian random variables. But what we have is a product of a Gaussian random variable times a Gaussian random variable. Now, this distribution is not Gaussian. In today's video, we'll see a method that can handle exactly this problem. Hi, my name is Bhargob Deka, and today I'm going to present the paper, The Gaussian Multiplicative Approximation for State Space Models. This article was recently published in the Wiley Journal of Structural Control and Health Monitoring. Today's video, the structure would be, in the beginning I'll explain the context of why we need this method, and then I'll explain the methodology. Then I will explain how to use this method through some numerical examples where and how this method is useful. And finally, I will end today's presentation through the key points of our method in the conclusion section. For the context, let's start with an intro for the Bayesian dynamic linear models. For example, if we have a temperature time series on the left, this can be decomposed into the three patterns that you see on the right. So what we have is a constant baseline, we have a periodic pattern, as well as we have the residuals that are captured by an autoregressive process. Now, all these three patterns are referred to as hidden states because they represent an underlying hidden structure for the observed time series. If we add these patterns together, we can get the observed time series. But also that we have each of these models or each of these hidden states have their own linear dynamic systems. Overall, Bayesian dynamic linear model is divided into two types of model. First is the transition model, where we model the transition of a hidden state at time step t-1 to t through a transition matrix A, together with a additive process error, which is modeled by a Gaussian having mean 0 and covariance matrix Q. For the observation model, what you do is we want to show the relationship of how these hidden states are associated with the observation itself. So we have the hidden states at time t, which are represented or which adds together to give the observation yt through the observation matrix C, together with the additive observation error V, which is again modeled by a Gaussian having mean 0 and covariance matrix R. So these matrices A, C, Q, and R are the building blocks for Bayesian dynamic linear models. But what about Bayesian dynamic nonlinear models? In general, any modeling of dynamic systems are referred to as state space models. Bayesian dynamic linear models are a subclass for state space models where we have linear transition and or observation models. Let's consider this new temperature time series. This also can be decomposed into the following patterns. So now we have a baseline that is evolving over time instead of being constant as we saw in the earlier example. And we have the same periodic pattern as well as the residuals captured by an autoregressive process. Now, if you look at this data, we cannot add these hidden states together in order to get the observations. What we have to do is we have to multiply the baseline that evolves over time, which is called the local trend. So we have the local trend times the periodic plus the residual in order to get the observations. Now this creates a nonlinear model. So we now have a multiplicative state space model because there is a multiplication of a local trend times the periodic, and this model for which we do not have an exact inference. The key findings of our method are we provide an analytical method for multiplicative state space models. We provide a way to perform online estimation for model parameters, which we will see through applied example section. We will also show how we can obtain new generic components. As you saw, that we can multiply a local trend times the periodic in order to get a new component that can model an amplitude that evolves over time. So we will see in the applied examples in details how we can obtain new generic components. And also in our paper, we show that we exceed the performance of Kalman filter, which is a nonlinear filter and also considered as a state-of-the-art. So we show that we are at least 4 times faster in terms of computational complexity. Before moving into the methodology section, I want to quickly go over the basic notations which I'll be using throughout the methodology section. So we represent the lowercase x to be a variable, the uppercase x to be a random variable, bold lower x to be a vector, or the upper bold x will be a matrix. We have y, which represents observation. So if we have a vector of random variables which has a Gaussian distribution, so we'll represent it in this way, for which the mu x and the sigma x represents the mean vector of x and covariance matrix of x. Let's consider a vector of hidden states where we have x1 and x2 as the variables, and this is related to a nonlinear function. So we have g of x, which is equal to x1 times x2, where we have an observation model where y is equal to g of x plus v, where v is again modeled by a Gaussian distribution having mean 0 and variance sigma square v. And this is what we presented earlier, and this is the observation model in which we have now a multiplicative or a nonlinear function where we have g of x equal to x1 times x2. So what is the goal now? So the goal is to infer x, or the distribution or the posterior distribution for x given y, which has to be obtained using the Bayes rule, for which we have the joint of x and y, the observations, divided by the evidence, which is f of y. Now, if we can ensure that the posterior distribution f of x given y is a Gaussian, for which the parameters would be mu of x given y and sigma x given y, we can ensure that we have a closed form solution. So we can obtain mu x given y and sigma x given y using through simple mathematical equations. So these are the equations that we can obtain using Gaussian conditional equations. Now let's look at the elements using which we can obtain these posterior moments. So we have mu of x, which will be given by the vector of expected value of x1 and expected value of x2. And we have mu of y, which is expected value of x1 times x2. This is where the nonlinear function comes, and we'll see how we can find this moment. Again, for covariance matrix for x, we have the variance of x1 and variance of x2 on the diagonal, and on the off diagonal we have the covariance between x1 and x2. So we do not have any nonlinear function, and we can obtain these terms. There is no roadblock for this. But when we have to calculate the variance of y, which is sigma square y is given by variance of x1 times x2 plus sigma square v. Now these two terms, expected value of x1 times x2 and variance of x1 times x2, these two terms we do not have. And this is the issue that will be solved using GMA. Now what is GMA? Gaussian Multiplicative Approximation, which is our method, also called GMA. We assume that we have two Gaussian random variables having the parameters mu1 sigma 1 square for one, and for the other mu2 sigma 2 square. Now the actual distribution for the product of x1 times x2 is unknown. There can be some simpler or known distributions for certain situations, but in general this is unknown. What we do is we approximate it to be a Gaussian distribution, and this is an approximation. What we have is, even though our distribution is an approximation, but you'll see how the moments associated with this distribution, which is the expected value of x1 times x2 and the variance of x1 times x2, are computed exactly. So these moments, expected value of x1 times x2 and variance of x1 times x2, which are the moments for the random variable x1 times x2, can be computed using these closed form solutions. And if you see closely, we only need the mean as well as the variance parameter for x1 and x2 in order to compute both these moments. This means that both these moments are a function of just the parameters for individually x1 and x2. We show the derivation of these exact moments using moment generating function as well as Taylor series expansion in the appendix section of our paper if you want to have a look. In a general situation, if we have a vector of random variables x1 to x4, so suppose we have multiple product terms. We can have x1 times x2, we can have x2 times x3, and so on and so forth. What we assume is each of those product terms to be a Gaussian distribution. Now, this is an approximation I want to state, and this is the only approximation we have. However, all the moments associated with those product terms are computed exactly, and there is no approximation to it. So on the right, you see the closed form equations for each of those moments. So we have expected value of x1 times x2, variance of x1 times x2, and the covariance between a hidden state and a product, or the covariance between two product terms. And on the right, those are put in gray because the equations doesn't matter. The equations are simple. We only care about the moments that are represented in blue. And these are the moments if we can obtain, so we can represent the product or the pair of product between any two Gaussian random variables by a Gaussian, and we have the exact moments available for that. Now, moving on from the methodology section, let's look at some numerical examples in order to see where we can have those product terms, or how do we use this method in general, or where will the opportunity come in order to leverage such a method. So let's consider with a simple example in time series modeling where we have observed time series and we can decompose it into a periodic pattern as well as we capture the residuals by a first order autoregressive process. Now, this is a basic step in order to do time series modeling. We decompose observed time series into the pattern and we capture the residuals. Now, to capture the residuals, we do it by modeling as a first order autoregressive process. Now, let's see how to model a first order autoregressive process. So, a first order autoregressive process is given by this transition equation where we have the hidden state for the autoregressive xAR at time t is equal to phi AR, which is the autoregressive parameter, times the hidden state at time t minus 1 plus the additive process error WAR. Okay, now if you see the equation, we have a parameter phi AR, or the autoregressive parameter. And what we do is we transform this transition equation into a set of new transition model where now we consider the parameter phi to be x phi. So it's a hidden state now and it transitions over time, and there is a constant value associated with that. This is what we assume. So that's why we have x phi at time t equal to x phi at t minus 1. So what do we do for the equation above, which is xAR? So now we'll have a product of x phi times xAR and plus the additive process error. So here you see the benefit of using the GMA. So we have now the product of two Gaussian random variables. So we have x phi, which is a Gaussian random variable, times xAR, which is also a Gaussian random variable. Now we can leverage our method GMA in order to obtain the moments for the product of this term. In general, the vector of random variables in order to model this process using so that we can learn both the XAR as well as the X phi together, we'll have XAR, so we'll have X phi and X phi times XAR. So this is the 3x1 matrix that we have where we will identify all these three terms together. So the mean parameter or the mean vector for this vector of hidden states or random variables would be the expected value of XAR, expected value of X phi, and expected value of X phi times XAR. Similarly, for the covariance matrix, only term that you need to focus are the terms in blue because all other terms are for single hidden state, whereas the terms in blue are the covariances associated with the product term. So we have a covariance of XAR, X phi times XAR, and we have X phi, X phi times XAR, and the variance of the product X phi times XAR. So now we have four terms to find, which are represented in blue. And these terms, we know that we can evaluate using closed form equations using our method. So once you can evaluate the mean vector as well as the covariance matrix at t-1 given t-1, we can move ahead and we can infer the posterior distribution for the vector of hidden states, which is X tilde. For an example, we simulated first order autoregressive process with phi AR equal to 0.9. So now our purpose is to identify the phi AR as a hidden state starting from some unknown prior knowledge. So to start the learning process, we started with these prior knowledge where we have 0, 0 for both AR as well as for phi and a variance of 100 for each. As you see, I have put a placeholder for the third vector because we saw that it was a 3x1 vector or 3x1 matrix. I provide a placeholder because we do not need to provide a prior knowledge for the product term, because as we saw earlier, it is a function of the mean and the variance parameters for individually the XAR and X phi. So using this, we will obtain our prior knowledge for the product term. So moving ahead, on the right, I present the figures for estimating both X phi and XAR together. Here I also compare with CKF, which is the Kubacher-Kalman filter, which I do anyways throughout for all the numerical examples in the paper. So we have in green, we show the uncertainty regarding the GMA. You see that the variability in the beginning is very high because it is trying to figure out what is the correct value for X phi. So once it is near the true value, it understands what should be the value or the value for XAR at that particular time step, and then both the GMA and the CKF moves together as shown by the overlapping of the uncertainty as well as by the predictions for both of these methods. And with the bottom graph, we see that we are able to identify the true value for X phi starting from a prior knowledge of 0 and a variance as large as 100. We have found out what is the true value for the phi. So this is a big benefit. Now we see that we had a parameter that has to be estimated before. Now we just provide a prior knowledge and the method will identify itself together with the other hidden states without changing anything, that what is the true value for those parameters. And now we can do everything together, so it makes an online process. So moving on from this example, let's look at some real life datasets or SHM-based datasets that we have. So here I present a flow rate dataset, which is from 2006 September to 2012 December. So if you look at this data set, you'll see that the amplitude grows over time. So we have to model it using a process that has the multiplication of a local trend times the periodic plus the residuals that you also see on the observed time series. So in order to model this, what we do is we replace the multiplication of a local trend times the periodic by one component called the trend multiplicative, which will be able to model this evolving amplitude over time, which is again a multiplication of a local trend that evolves over time, basically a baseline that evolves over time, times a constant periodic pattern, because of which the amplitude increases over time. And this is our forecast using this new component trend multiplicative, where we are able to identify the evolving amplitude over time, where the red line shows the actual observation, the black line shows our prediction using GMA, as well as the green bound shows the uncertainty associated with our prediction. Now, this prediction was obtained using the following hidden states. So we have the constant periodic pattern, as I mentioned, that we had to multiply two hidden states. So one of which is periodic pattern. So we have the periodic pattern represented by XS1. So this is the hidden state times XLP. So XLP is the baseline that is evolving over time. So when we multiply XLP times XS1, we get a amplitude that is evolving over time, as you see in the bottom figure. And this is what we intend in order to model the time series or the flow rate time series in the previous slide. So now we have a component that we can do this. So whenever we see a pattern that is appearing, or whenever we have a time series where we see such kind of pattern, we can leverage this new component in order to model this feature. Let's look at one more time series. Now this is traffic load dataset, so which is in 2007 from September 1st to October 21st. Now if you look at this observation closely, you'll see that there are two periodicity that are being multiplied together. One periodicity is for 7 days and one has a 1 day periodicity. So if you multiply these two periodicities together, you will see something similar to that. So now what we want to do is to model this multiplication of these two periodic patterns, which can be modeled using a kernel regression component, which is already available in the BDLM framework. So we'll replace the multiplication of these two periodic patterns using a double kernel regression. On top of that, we'll add the residuals that you see in order to get the observed time series. And this is the prediction that we have using GMA. You see that our predictions are so accurate compared with the real data, where the real data is shown by the red solid line, the black line represents our predictions, and the green bound shows the uncertainty associated with our predictions. These predictions were obtained using these following hidden states, where we have XKR1 that represents the hidden state associated with the periodic pattern having a periodicity of 7 days. So we model this using a kernel regression component. XKR2, we model this by we model the periodic pattern having a periodicity of 1 day using again a kernel regression. And finally, we perform the product of XKR1 times XKR2 to give the pattern that we see in the observation. So we again have a new generic component for which we have replaced the multiplication of two periodic patterns. On top of that, we have also evaluated the X phi online, as we saw in the first numerical example. So we had no idea regarding what the phi AR parameter should be, and usually you have to optimize it using Newton-Raphson. But taking advantage of our method, we provide a prior knowledge for the x phi and want it to learn together with all other hidden states. And we see that it learns over time and the uncertainty diminishes as it identifies the true value. In this practical situation, we have no idea what the true value is because this is not a simulated data, but the method identifies what should be the correct value for the phi AR as shown by the diminishing of the uncertainty as it learns over time. In conclusion, we provided a method that can perform analytical inference of the mean vector and the covariance matrix for the product of two Gaussian hidden states. We saw in numerical example 1 as well as in numerical example 2 that we can perform online estimation of the model parameters as Gaussian hidden states as shown by the autoregressive parameter, which was assumed to be a Gaussian random variable and was learned together with all other hidden states. Similarly, we can do it for other parameters that appear in our transition or observation matrix or observation model, where we see there is a multiplication of a parameter and a hidden state. We can now transform that parameter as a hidden state and learn both these states or all the states together online. As we saw, we can create new generic components in the BDLM framework using the components that are already available. So we have a lot of components that are available in order to model periodic pattern, to model baseline evolving with time. Using our method, we can create new components. For example, we showed in example 2 that we can perform the multiplication of a local trend times the periodic to get one component called the trend multiplicative. Similarly, for the next problem, we show that we can multiply a periodic times a periodic in order to get a component called double kernel. So we can create new generic components. And in our paper, we show that we exceed or match the performance of Kalman filter in the SHM-based case studies that are shown, which is the numerical example 2 for the trend multiplicative and the numerical example 3, which is the double kernel. And the details regarding the state estimation as well as other results are provided in details in the paper, and also the proof for the GMA, also the equations using both moment generating function and Taylor series expansion are provided in the appendix section of the paper if you want to have a detailed look. Finally, Gaussian Multiplicative Approximation or GMA is a missing piece to the puzzle of analytical tractability for multiplicative state space models. Thank you. If you have any further questions, you can write to me. It will be my pleasure to help you. Thank you.